Einstein's Theory of General Relativity and Its Applications by Spencer Kelly. So the organization will include preliminaries and then we'll get into general relativity and its applications. So first off, Einstein's theory is heavily dependent on high-level mathematics, most of which are far out of the scope of our curriculum thus far, but we will introduce and define two of the branches and how they are used in the theory. So topology is the first one and is a branch of mathematics that is concerned with the properties of space that are preserved under continuous deformations such as stretching, crumpling, or bending, but not tearing or gluing. And it allows us to do math, the fabric of space, which is why it's so useful to GR, and it first began to be recognized for its usefulness in the 20th century. And here's a quick illustration and a quote. And then tensor calculus is an extension of the ideas of classical vector calculus to include tensor fields, which are tensors that may vary over a manifold, and it's useful to general relativity because space is considered a manifold, and being able to use tensors with it simplifies a lot of math. And it also allows the choice of any coordinates on the manifold, meaning that the form is invariant. And then here are a couple of quick illustrations. Then now we're getting into general relativity. So Einstein first published his theory of general relativity in 1915, and similar to Newton's, it is just a theory of gravitation, and it is now how gravitation is described in physics today. So the tenets of general relativity, we know that it is founded on two important concepts: the principle of equivalence, which states as follows: there is no experiment that can be done in a small confined space that can detect the difference between a uniform gravitational field and an equivalent uniform acceleration. Then the second concept is that spacetime must be curved as a result of gravity. Tests of general relativity. So there were multiple experiments conducted that proved general relativity was correct. We're going to cover the bending of light, the perihelion shift of Mercury, and light retardation. So the bending of light / gravitational lensing was conducted in May 1919 by Arthur Eddington. He used a total solar eclipse to find out whether or not light would be bent around the sun. Einstein's theory predicted a deflection angle of 1.75 seconds of arc, and two measurements found 1.98 plus or minus 0.16 and 1.61 plus or minus 0.4 seconds, thus proving Einstein correct. And further experiments have been conducted since using starlight and radio waves from quasars, which further prove Einstein's theory with ever-increasing accuracy. So the perihelion shift of Mercury is something that had been known about since the 19th century, and it's due to a gravitational perturbation that accounted for 575 arc seconds per century. In 1859, Leverrier announced that even with this taken account for, there was still a shift of 43 seconds of arc per century, and Einstein's theory predicted a perihelion shift, and his calculation showed that it was exactly the 43 seconds of arc that were missing from Leverrier's calculation. So light retardation occurs when light passes by a massive object and takes longer to reach a position due to the spacetime curvature caused by gravity. Erwin Shapiro sent a radio signal to Venus and had it come back, and he measured a time delay of approximately 200 microseconds, further proving Einstein correct. And some applications of general relativity are GPS and further use for science, but specifically astronomy. So Global Positioning System, or GPS, is an array of 24 satellites with atomic clocks inside that was originally built for military navigation. So since they're 20,000 kilometers above the surface of the Earth and move at 14,000 kilometers an hour, the clocks don't tick at the same rate as those on Earth. Relativity is used to account for the rapid movement and weaker force of gravity the clocks experience. And without taking note of relativity, inaccuracy of position could accumulate to up to 10 kilometers per day. So relativity in astronomy predicted the gravitational waves, the expansion of the universe, and also the best way to describe the Big Bang. So gravitational waves, which are ripples in the fabric of space-time, were first experimentally discovered in the spring of 2016. The expansion of the universe is important in astronomy because it means that everything is moving away from everything else, which is something that astronomers need to take note of. And lastly, relativity is able to describe the Big Bang because in this theory, there was a point billions of years ago where all the energy of what is now the universe was compacted into one tiny point. E equals mc squared allows for the conversion of pure energy into mass. So in conclusion, relativity might not have any real-world applications or many real-world applications, but it's still one of the most elegant theories in science. It continues to stand the test of time as more gravitational waves are being discovered, and it's further proving its excellence. And there's still a quest to unite relativity and quantum theory in what is called quantum gravity, or the theory of everything. Thanks for watching, and here's a quick works cited.